Okay, let's go ahead and get started. So first of all, I wanted to ask just a procedural question. So I was going through and seeing how many weeks we have left in the semester and how many problem sets I have left to assign. I have 2 problem sets I would like to assign. Given that I would not have a problem set due the last day of class, meaning during exam week, I think I'm not even allowed to have problem sets due during exam week. That gives me 3 Mondays left on which I could have problem sets due, yet only 2 problem sets to hand out. So that means that I could either continue handing them out weekly, or I could give you a week off. I could give you a week off at the end, or I could give you a week off now.
Week off at the end.
At the end? Okay. Would you appreciate that? Okay. So what I'll do is I'll continue having problems. I'll hand out a problem set next class, which will be the following Monday, and then again for the following Monday. But then on the Mondays in April, you probably won't have problem sets too. Unless I'm really inspired and think of another problem set. That's tempting. Maybe I won't do that just because I'm a kind and benevolent dictator. Okay, good. Let's go ahead and do some physics. So last time we began our discussion of systems with many degrees of freedom. So in particular, I made the following claim, which is that for a system with n degrees of freedom, the dynamics of small excitations around a stable equilibrium is given by n independent simple harmonic oscillators. And the frequencies of the harmonic oscillators, the frequencies of these small excitations, depend on the details of the system. And I gave you an explicit procedure last class for constructing these oscillatory modes and for solving for the corresponding frequencies. In particular, we considered a system with n degrees of freedom, Qi, where I ran from 1 up to n. And we considered a rather general sort of Lagrangian with a kinetic term given by Tij, Q dot I, Q dot J, summed over I and J, where this Tij was thought of as an n by n matrix of functions of the dynamical variables, which describe the kinetic energy of the system. So, of course, for a collection of n freely moving particles, this kinetic energy matrix will just be a diagonal matrix whose diagonal entries are constants and given by the masses of the particles. But for more complicated systems, where the QIs are not just the linear positions of particles, the kinetic energy matrix can be more complicated. For example, if you have a rotating system, then you might have a kinetic energy term which looks like r squared theta dot squared, in which case you would have a kinetic energy matrix with a component which looked like r squared. And in addition, we had a potential which was also a function of the dynamical variables. Now, I should mention that this is a very general sort of Lagrangian, but it's not the most general Lagrangian that I could write down. For example, I could also imagine having terms which are linear in Q dot, rather than quadratic in Q dot. Such terms do indeed arise for certain systems, The prototypical example of a system where a term which is linear in Q dot rather than quadratic in Q dot arises is a charged particle moving in an electromagnetic field. And indeed, not on this problem set, but on the following problem set, and the problem set after that, you will encounter several examples of systems where you have terms in your Lagrangian which are linear in velocity rather than quadratic in velocity. So you should keep in mind that although this system that I have written down is quite general, it is not, of course, the most general Lagrangian that it is possible to write down. So this kinetic energy matrix had two properties. It was symmetric and invertible. And using these properties, we proceeded to study the dynamics of this system expanded about an equilibrium solution. So an equilibrium is a configuration with Q equal to a constant such that the derivative of the potential, so that is a set of n quantities, you could think of it as an n-dimensional gradient, is equal to 0 at Q naught. And then one can write down the equations of motion in a perturbation around Q naught. So we called eta I the small perturbations around the equilibrium configuration. And we saw that the equations of motion expanded to linear order in the eta I's said that eta dot, where I think of eta as an n-component vector, was equal to minus T inverse V double prime eta. Yes?
Just the subscript of Q, an equilibrium configuration with...
Yes. Evaluated at Q naught. So V is a function of the Q's. dV by dQi is an n-component vector. And then we evaluate that vector at a particular point.
But I want the subscript, and they call it Q sub something I.
Sub Q naught I. So so this is a notation that people sometimes use where if I write a bar with a subscript, then I evaluate that thing at a point. So Qi is equal to Q naught I. So okay, that's a squiggly line because I wrote it as a subscript and then I changed my mind and wrote it as a superscript. Thank you. Okay. Yeah. So if we think of eta as an n-component vector, then T is an n by n matrix. T inverse is also an n by n matrix. And V double prime is the Hessian matrix. So it's the n by n matrix whose components are the second derivatives of the potential with respect to Q, often called the Hessian matrix. And so, in order to analyze the dynamics of the system, we look for the eigenvalues of this matrix, which I also called F last class. And so we look for eigenvalues of that matrix. In particular, we look for eigenvectors, mu A, where A runs from 1 up to n, because an n by n matrix has n eigenvectors, which obey the eigenvalue equation F as a matrix acting on mu A is equal to minus omega A squared mu A, which is the same as the statement that omega A squared T mu A is equal to V double prime mu A. And then, if we expand eta in terms of these eigenvectors, so if we just let eta A be the component of eta pointing in the direction of one of these eigenvectors, then the equations of motion are eta A double dot is equal to minus omega A squared eta A. So eta A, the component of the perturbation in one of these directions, obeys the equation of motion of a simple harmonic oscillator with frequency omega A. So if the omega A's are all real, then the equilibrium is stable, and the dynamics is that of n independent harmonic oscillators. Now, there's a special set of names associated with this. The omega A's are the normal frequencies of the system, and the mu A's are the normal modes. So what I would like to do now is just present to you an alternative way of reaching exactly the same conclusion, that the dynamics can be described in terms of n simple harmonic oscillators. Before I do so, are there any questions about what we covered last class? So the analysis that I just reviewed for you was an analysis where we wrote down the equations of motion and then expanded them to linear order in the small perturbation. I think it's probably instructive to see that, in fact, we can derive the exact same conclusions directly from the Lagrangian. So rather than writing down the equations of motion and expanding them in a power series in eta, we could instead look at the Lagrangian and expand them in a power series of eta and show that the Lagrangian is just the Lagrangian for n independent simple harmonic oscillators, at least for very small perturbations around an equilibrium point. And that's what I would like to show you now. So just to remind you, the Lagrangian is 1/2 the sum over I and j, Tij, q dot I, q dot j, minus v. And we expand qi is qi naught plus eta I. And now we wish to take this, plug this into the Lagrangian, and expand order by order in eta. So what happens when I do this? So now this is just an exercise in Taylor's theorem. So there will be a term which is independent of eta, order eta to the 0, which will just be a constant. And of course, we don't care about adding an overall constant to the Lagrangian because that doesn't change the equations of motion. And then there will be a term which is linear in eta. And before writing down the term which is linear in eta, it's useful to pause and think what we expect the answer to be. So what is the term that is going to be linear in eta? So Q naught is a solution to the equations of motion. And eta is a small perturbation around a solution to the equations of motion. So the term which is linear in eta will describe the variation of the Lagrangian to first order in a small perturbation around a solution to the equations of motion. So we had a name for the first variation of the Lagrangian around a solution to the equation of motion. We called it the Euler-Lagrange equation, or the equation of motion. And that vanishes for a solution to the equations of motion. So that means that if you wrote down the term which is linear in eta, expanded around Q naught, you would find something which vanishes for solution to the equations of motion. Indeed, let's stare at this expression for the Lagrangian and imagine expanding it to linear order in eta. Well, the kinetic term will obviously only contribute things that are quadratic in eta because of the time derivatives. And so what we get is, by Taylor's theorem, minus the sum over I dv by dqi evaluated at q naught times vi, or times eta I. And indeed, that is equal to 0 for an equilibrium configuration. And, right, because an equilibrium is defined to be a point where the derivatives of the potential vanish. Yes?
Why did you not eta naught I?
Oh, it's eta I, because I'm expanding this potential using Taylor's theorem. Plugging in Q is Q naught plus eta. That had to be the case. And indeed, here, even if you hadn't known it was the case, you would have quickly seen that it was the case as soon as you wrote it down. But, this is by construction. The whole point about an equilibrium is that, the whole point about a solution to the equations of motion is that the term in the Lagrangian, which is linear in a perturbation around the equations of motion, vanishes. That's how we derive, that's Hamilton's principle. That's the principle of least action. Any questions on that? Okay, good. So the 0th and first order terms in the expansion are just irrelevant. One of them is a constant and the other is 0. So let's look at the second order term. So there'll be two terms. 1/2 the sum over ij, tij now evaluated at q naught times eta dot I, eta dot j. And then a term which comes from expanding the potential. So that will be the derivative of v with respect to qi and qj times eta I, eta j, evaluated at q naught. And that is just the second order term in the Taylor expansion of v. Or, if we wanted to use our vector notation, that is just 1/2 eta transpose times the matrix T times eta minus eta transpose times the matrix V double prime times eta. Where here I think of eta as a column vector and eta transpose as a row vector. So this gives me the number which is the same as this sum that I wrote above. Sure, you could write that. You could write it as eta transpose T minus V double prime times eta if you wanted to. But I'm writing it this way for reasons that will become useful in a minute. Any questions on this before I continue? Okay, so now what we do is we imagine expanding eta written in terms of the basis of eigenvectors of that matrix F, which means we write eta as the sum over A, eta A, mu A, such that the mu A's are defined as the eigenvalues of the matrix F, which I remind you was the statement that omega squared T acting on mu was equal to V double prime acting on the vector mu. Okay, so let's just plug that in to our expression for the Lagrangian. So let me just drop the constant because that's not going to affect anything. So For each eta and eta transpose, yes. I'm sorry, there are dots there. Yes. Sorry about that. Thank you. There are dots there. That's a kinetic energy term. Yes. Sorry about that. Everyone with me on that? Yes. If I make a stupid mistake like that, please correct me. Even if I make an intelligent mistake, please correct me. But especially if I make a stupid mistake. Okay. So let's plug that in. So the Lagrangian is 1/2 times the sum. Now we need to sum over A and B, because I'll have to expand both eta and eta transpose as a sum over A and a sum over B, respectively. Well, what is that first term? That is mu A transpose times T times mu B. And the second term is mu A, times eta A dot, eta B dot. And the second term is mu A transpose V double prime mu B times eta A, eta B. Everyone with me on that? I'm just inserting the expansion of eta in terms of the eigenvectors into our expression for the Lagrangian. Now I can use this expression up here and plug it in to V double prime acting on mu B, and write this as 1/2 times the sum over A and B of mu A transpose times T times mu B times eta A dot, eta B dot, minus omega B squared, eta A, eta B. So all I have done there is replace V double prime mu B by omega B squared T mu B. So this is looking pretty good. So let's stare at this term right here. Now note that if A were equal to B in this expression, this would be the Lagrangian for a simple harmonic oscillator for the variable eta A. Right? It would be eta A squared, eta A dot squared minus omega A squared, eta A squared. And I will now make the following claim. Mu A transpose times T times mu B is equal to 0 unless A is equal to B. Yes? No, I just, here? So I just used this equation right here. Yeah. Any other questions? Okay. So let's prove this. So here I'll have to use the equation for the eigenvector, along with the fact that the T and V double prime matrices are symmetric. So let me write down this eigenvalue equation. So I'll write it as omega B squared T times mu B is equal to V double prime mu B. So that's just the eigenvalue equation. And I could take the adjoint of this equation, or take the transpose of this equation, and write this as omega B squared times mu. Well, let me take the transpose of this equation. Here, let me write it like this. So the transpose of this equation is omega A squared mu A dagger, so the adjoint of this equation rather than the transpose. Of course, everything's real, so it's the same. But I haven't proved that to you. So let's just take the adjoint. So the adjoint of this equation is omega a squared mu a dagger times t is equal to, sorry, there's a mu b there, mu a dagger v. So I've replaced the a by the b index there. I am free to do that. A and b are just indices that run from 1 up to n. I can call them whatever I like. So let's look at those two equations. So I used in writing down that adjoint equation that t and v were real and symmetric. So t adjoint is equal to t and v double prime adjoint is equal to v. So let's multiply that first equation by mu a dagger on the left. So that's omega b squared mu a dagger t mu b is equal to mu a dagger v double prime mu b, and likewise multiplying this second equation by omega b on the right, I have omega a squared times mu a dagger t mu b is equal to mu a dagger v double prime mu b. So we can compare those two expressions and subtract them from one another, and we see that omega b squared minus omega a squared times mu a dagger t mu b is equal to 0. And so that means that as long as our eigenvalues are distinct, mu a dagger t times mu b is a diagonal, vanishes unless a is equal to b. So that's what I claimed was true. So if the eigenvalues are distinct, then the Lagrangian is just equal to the sum over a, mu a dagger t times mu b, mu a, times eta a dot squared minus omega a squared eta a squared. So mu a dagger t times mu a is just some number, and multiplying a Lagrangian by an overall constant doesn't affect the equations of motion. So we see that the dynamics is exactly that of n simple harmonic oscillators with frequency omega. So I would like to conclude by making a few other remarks about this system. Before I do so, are there any questions? Okay. So the first comment I would like to make is that if two eigenvalues are equal, then the derivation doesn't work, and we say that the system has a degeneracy. And so in this case, the dynamics are more complicated. Indeed, if you look in your textbook, there is a worked out example of a system with a degeneracy. I encourage you to go through that. It's a useful exercise. And indeed, if I can think of a good exercise for one of your problem sets, I probably will put something involving a degenerate system for you to work out on your problem set. Because spiritually, the problem is very similar to that of a non-degenerate system. You just have to think a little bit, which is always an interesting exercise. Okay. The other comment I would like to make is that if one of the eigenvalues vanishes, then we say that the system has a zero mode. Because one of the frequencies of the normal modes is equal to 0. So in that case, the system actually has a symmetry. So if you look at the Lagrangian up here, and you imagine that one of the frequencies, omega A, vanishes, then the system has a symmetry. Sorry, that's not a very neat spelling of symmetry. God damn it. Okay, it has a symmetry where eta A goes to eta A plus a constant. Because the Lagrangian is in that case independent of eta A and depends only on eta A dot, which does not change if you shift eta A by a constant. And so because of that, there is a conserved quantity, and the conserved quantity is very easy to understand. You can think of eta A as a position, and if the Lagrangian is independent of position, then there is a conserved linear momentum, which in this case is just eta A dot, which you could think of as PA. The momentum conjugate to eta A is a constant. Indeed, if you just write down the equations of motion in that case, it would say that eta A double dot is equal to 0, or eta A dot is equal to a constant. So if the system has a zero mode, then eta dot is equal to a constant in the direction of that mode. Now, I should emphasize, however, that we have been working only in the approximation where eta is very small. And so this symmetry may or may not be present at higher orders in eta. So if you are lucky, then this is a reflection of a true symmetry of the system. And in fact, the Lagrangian expanded to order eta to the 27 will still be invariant under shifts in eta. But sometimes it will not be the case. It will only be an accident that the linear and quadratic terms vanished in the Lagrangian, but the higher order terms may not. And so that's just something you have to determine on a case-by-case basis. And so in the next few minutes, I'll describe a couple examples, including one example where we have such a zero mode, which indeed does come from a full symmetry of the system. So I would now like to work out a few examples of normal modes and normal frequencies for some systems of interest. But before I do so, let me pause and see if there are any questions. No questions? Okay. So let me consider one of my favorite mechanical systems, because it's one of the only ones that I can remember, which is that of a double pendulum. I swear I must have worked it out the Lagrangian for the double pendulum at least a couple times in this class before. So the double pendulum consists of a pair of linked pendulums. Let's just take the lengths of the two pendulums and the masses of the objects at the ends of the pendulum to be equal. And I will take as my dynamical variables the angles that the two pendulums make with vertical. So I'll call those angles theta 1 and theta 2. Then the Lagrangian is easy enough to write down in terms of theta 1 and theta 2. Sorry, is that picture clear enough? Can you guys all more or less read what I've written there? Yeah. So what is the Lagrangian? Well, the Lagrangian in terms has various kinetic terms involving theta 1 dot and theta 2 dot. So there's a theta 1 dot squared term, which is has a coefficient m squared L squared times theta 1 dot squared. A theta 2 dot squared term, as well as a term which is proportional to theta 1 dot times theta 2 dot. And a potential term which involves theta 1 and theta 2 as well. So I believe I worked out this Lagrangian for you in class several weeks ago. Perhaps you don't want me to work it all out again. It's a straightforward exercise to just writing out the kinetic energy of the various parts of the pendulum and the potential energy of the various parts of the pendulum, and writing them in terms of theta 1 and theta 2. Any questions on that so far? There is no 1/2 on the first term. Who can tell me why there's no 1/2 on the first term? But I'll tell you why there's no 1/2 on the first term. There's no 1/2 on the first term because what's that? Because at the end of the day, let's imagine keeping theta 2 constant and just changing theta 1. Then the position of both masses change. And so, in fact, there's effectively 2m there instead of 1. I encourage you to go back to, I believe, the first week of lectures when I derived the Lagrangian of the double pendulum. Perhaps it was the second week of lectures. Question? What can I say? I derived this Lagrangian in the first week of lectures. Okay, let's say that you don't. Okay, if you don't believe me, then well, there's not much I can do to help you, except tell you to work out the Lagrangian yourselves. Let's not pay too much attention to the individual factors of 2 and stuff that appear there, because what I'm really trying to do is evaluate this in perturbation around a small equilibrium. So let's consider the equilibrium point where theta 1 and theta 2 are equal to 0. And this will be a stable equilibrium because, as you can just see by thinking about the double pendulum, a small perturbation around the equilibrium where theta 1 and theta 2 equal 0 will not grow in time. And indeed, one can check this by computing the normal modes and the normal frequencies, which I will now do. So first, let's write down the kinetic energy in the Hessian matrix of the system. So what is the kinetic energy matrix? Well, it's m L squared over 2. So what is so here Qi is a 2-component vector with components theta 1 and theta 2. And then from this Lagrangian, we can read off the kinetic energy matrix. So the T11 component is the coefficient of theta 1 dot squared, which is m L squared. So I'll write that as m L squared over 2 times 2 in the T11 component. The T22 component will be just 1/2 mL squared. And the T12 and T21 components are taken to be equal because I write the kinetic energy matrix as a symmetric matrix, and they will both be equal to 1/2 ml squared times the cosine of theta 1 minus theta 2. So I remind you that, of course, I could write the kinetic energy matrix as something not symmetric, but I can also choose to write it as a symmetric matrix, in which case I need to write the T12 and T21 components as 1/2 ml squared cosine squared theta, so that their sum, the T12 theta 1 plus T21 theta 1 dot theta 2 dot terms, will give me this cross term in the kinetic energy matrix. And then I need to evaluate this at the equilibrium point where theta 1 and theta 2 are equal to 0. So that is ml squared over 2 times the matrix 2, 1, 1, 0, 2, 1, 1, 1 at the point where theta 1 and theta 2 are equal to 0. Questions? Okay, let's compute the Hessian matrix. So the potential is MGL times 2 cosine theta 1 plus cosine theta 2, and V double prime sorry, there's a minus sign there, I guess. Okay, I'm sorry, there was a minus sign up here, actually, because I defined my theta 1 and theta 2 to be equal to 0 if the system was if the pendulums were pointing down rather than up. So there's actually a minus sign there, right? Because the potential should be positive if the potential should be no, I'm sorry, there's no minus sign there. Right, the potential is very negative. Okay, good. I take it back. Yeah, so there's a minus sign there. So what is the Hessian matrix? Well, we have MGL times the second. So what is the V11 is the second derivative of V with respect to theta 1, which is minus 2 cosine theta 1. So that cancels the minus sign out front. The off-diagonal components are the derivatives, the second derivatives of V with respect to theta 1 and theta 2, which are equal to 0 because there are no cross terms. And the 2 component is the second derivative with respect to theta 2, which is cosine theta 2. So at the stable equilibrium point, this is equal to 2, 0, 0, 1. So the equation of motion, then, is T acting on the vector theta 1, theta 2, double dot, is equal to minus V double prime acting on the vector theta 1, theta 2. Or 2, 1, 1, 1 acting on the vector of theta 1s, of theta double dots, is equal to minus G over L acting on the vector 2, 0, on the vector 2, 0, 0, 1 times theta 1, theta 2. So I've just divided through both sides by ml squared over 2. Yeah, I think I must have missed a factor of 2 somewhere. Okay. Over 2. I must have been having a bad day when I wrote these notes. Is it on the numerator? Yes. Thank you. Oops. So it's then a straightforward procedure to work out the eigenvalues and the eigenvectors. So the equation of motion is theta 1 double dot, theta 2 double dot. We just invert the matrix 2, 1, 1, 2, and multiply that times the matrix 2, 0, 0, 1. Question? Yeah. And so let me just write down the answer for you. So you have to divide by the determinant of the matrix, which is 2. And if I've done the math correctly, you get 2. So there's a minus sign, 2 minus 1 minus 2, 2. And this is the matrix that we would have called F. I'm sorry, 1, yes. So is there an overall factor of 2 I missed? That's always possible. Okay. You should never... Okay. I'll let you check that for yourselves. Did I get that right? Yeah. Yes. Okay, I think that's right. And so then it's a straightforward procedure to find the eigenvalues and the eigenvectors. So I'll just write them down for you. So there's an eigenvalue, eigenvector 1 root 2, whose eigenvalue is, well, there's going to be a G over L, of course, because of the overall G over L in the matrix, times 2 minus the square root of 2. And a second eigenvector, whose eigenvalue is given by the opposite sign. So perhaps you will forgive me if I don't derive these eigenvalues and eigenvectors explicitly. I'm sure in your linear algebra class you had plenty of practice deriving the eigenvalues and eigenvectors for simple matrices such as this. Is everyone comfortable doing that? If you're not, all you do is you write down the characteristic polynomial, which in the case of a 2 by 2 matrix is a quadratic polynomial, and you find its roots, which is why I have these 2 roots here, which are related by a change of sign, and then you write down the equation for the eigenvectors, and you solve that equation. And it's, yes?
Do you care about normalization?
I don't really care about the normalization of the eigenvectors. No. Why would I care about the normalization of the eigenvector? Because the eigenvector equation doesn't depend on the normalization. You could take them all to be unit normalized if you like, but that's just, that's just a personal preference. So what's important, however, is the interpretation of the results. So first of all, as I claimed, both of those frequencies are positive. And indeed, by looking at the behavior of these modes, you can understand physically what the excitations of the system look like. So there is the mu1 normal mode, which has lower frequency. So what does it mean for a mode to have lower frequency? That means that the excitations have lower energy, and so they're easier to excite. So generally speaking, a system will have more motion generically in the degrees of freedom with lower frequencies. And what does that look like physically? Well, that corresponds to the motion where theta 1 and theta 2 are both either increasing or decreasing at the same time, just because mu1 contains 2 positive numbers. And indeed, that just describes a uniform motion of the two masses that make up the double pendulum. Whereas the higher frequency mode describes motion where the two ends of the pendulum are moving in opposite directions. Now, in order to understand this intuitively, I would just like you to close your eyes and imagine that you are holding a double pendulum in your hand. And if you've ever held a double pendulum, then you will understand that there is a low frequency way of oscillating the double pendulum so that the two ends of the double pendulum oscillate uniformly, just as if you had a single pendulum. And there's also a high frequency way of doing it, where the two ends of the pendulum move in opposite directions. And so that's just precisely what we've derived here in terms of the normal modes and normal frequencies of the pendulum. Are there any questions about this derivation? Yes. Did I get don't ask me if I got some number wrong. If I got a number wrong, here,
I think there's
is there some factor of 2 I missed somewhere?
I think there's something wrong with f, because the eigenvalues of f seem to be 2. Because if you do the characteristic, oh no, never mind, sorry. I just don't know how to do that.
Okay.
My fault.
Any other questions? Okay. If there are no other questions, let's move on to a slightly more sophisticated example, which is probably a bit more of a prototypical example where this business in terms of normal modes and normal frequencies is interesting. So let's consider a molecule, such as carbon dioxide. Now, you may or may not remember from your chemistry classes that a carbon dioxide molecule is linear. So you have a big mass, which is carbon, and two little masses, which would describe oxygen, that are arranged in a symmetrical manner about the carbon dioxide center. So let's call the mass of the central. What is the atomic mass of oxygen? Okay, so I got it wrong. It's the other way around. So I said such as. That's what I thought. Okay. So let's consider a molecule such as carbon, but not actually carbon, where the central mass is bigger than the other masses. Or you could take it less than. I'm just going to write down a bunch of equations. I'm not going to actually use the fact that one mass is bigger than the other. But I guess I drew it wrong if I were going to draw a carbon dioxide molecule. Okay, let's call it, what's some heavier thing which binds with? Silicon dioxide. Excellent. Okay. Silicon dioxide. Okay, good. Jesus Christ. This is a physics class, ladies and gentlemen. This is not a chemistry class. Okay. So how would we like to model this molecule? Well, let's denote the positions of these three atoms as x1, x2, and x3. And let's take the interaction between these molecules to be, well, we don't know what that interaction potential will look like, but we do know that there will be some sort of stable equilibrium of that interaction potential, where we have some rest lengths, let's call them L, between the various atoms. And we know that whatever that interaction potential looks like, it should be, we could Taylor expand it around this minimum, and it will have terms which are quadratic. The linear terms will vanish because that's what it means to be in a minimum. And so what that means is that to lowest order, effectively, we can think of those two links between the carbon or the silicon and oxygen atoms as harmonic, as springs. And the potential can be written in terms of some spring constant So we'll have an x1 minus x2 interaction and an x3 minus x2 interaction. Or if you like this, I could write this as x2 minus x1 minus L, if that would make you more comfortable. Because, you know, my aim here is to make you comfortable. And the kinetic energy matrix, well, that's just the matrix M, big M, little m. So we can then proceed to imagine the small perturbations of the system by perturbing, for example, in x1, x2, and x3. So a vector perturbation will be the three-component vector whose components are the perturbation in x1, x2, and x3, respectively. And so it's now a straightforward exercise to compute, for example, v double prime. So, of course, there will be a k over 2 out front. So v double prime 1, 1 will be 1. Well, I guess there's a half there, isn't it? Jesus Christ. Okay. So there's no 1/2 there. Okay. So there's a 1 in V11, as well as a -1 in V12. There's no 1,3 cross term. So there'll be a -1 here by symmetry. A 2 here because there are two x2 squared terms that we are adding up. And a -1 here because of the x2, x3 term. There's no x1, x3 interaction. And then a -1 here by symmetry, and a 1 again coming from the x3 term. Did I make any mistakes? I don't think I made any mistakes there. So the equation for the normal modes and frequencies is just the usual equation for the eigenvalues and eigenvectors of the matrix F, which is minus T inverse times V double prime. So we have K times minus 1 over m and 1 over m in the first row, 1 over big M and minus 2 over big M and 1 over m in the second row, and 0, K, 1 over little m and minus 1 over little m in the third row. And then it's a straightforward exercise to determine the normal modes and normal frequencies of the system. So who can tell me what the lowest normal frequency is? Well, there are two ways to proceed here. One way is to write down the characteristic polynomial for the frequencies and find its roots. The other way is to think. So you may notice that the system that I described above has a translation symmetry. And because of that, that means that you are guaranteed to find a normal frequency which is equal to 0. And what is the corresponding normal mode? Well, it's going to be the 0 eigenvector of this matrix. And even before you try and find the 0 eigenvectors of this matrix, you can just think and write down what the answer is. It'll be the vector 1, 1, 1. Why? Because that's the thing that describes a uniform translation of all three atoms at the same time. So this describes a translation mode where all three of the constituents are moving uniformly. Now, the other two modes, there's no recourse but simply to compute the eigenvalues and eigenvectors of the matrix. So the next lowest mode has frequency k over m, and the mode is 1, 0, minus 1. So that is a nice physical-looking thing. That just describes the situation where the central atom is stationary and the two outlying atoms oscillate in phase. So this would be a case where the mode is symmetric, has a left-right symmetry. So we would call that the symmetric mode. And then there's a third mode, which has even higher frequency. That's totally not obvious. You just sort of have to do the computation. I'll write down the answer for you. And so you can see that that mode is anti-symmetric. So that describes the case where the two right-hand atoms are moving closer to each other, where the two left-hand atoms would be moving closer to each other, whereas the right-hand one is moving farther away. Or if you wait a little bit, the left-hand ones would be moving closer. The right-hand ones would be moving closer to each other, and the left-hand one would be moving farther away. So this would be an anti-symmetric mode.
The middle atom?
It's wiggling the middle atom, but at the same time, the other atoms will be wiggling as well.
Okay.
It just so happens that when you find the normal modes, there is not a normal mode where the central atom wiggles independently of the other two. Or another way of saying that, if you started out with the system and you started wiggling the central atom, it would cause motion in the other two atoms. In particular, as you wiggled one of them, the other two would wiggle in response. They would wiggle out of phase, in phase, according to this this computation. So this sort of computation that I did for the very simple case of the linear triatomic molecule is the kind of computation that is very often extremely useful when analyzing atomic systems. So, for example, on your problem set, you will analyze other sorts of molecules with different geometry. Very frequently, you'll find people who are studying materials physics writing down a model for the crystal structure of some material, and then computing the normal modes by looking at the oscillations of that crystal in exactly the same manner as I have described here. I should also emphasize one additional point here. So, at the end of the day, if I were to hand you a given mechanical system and ask you to find the normal modes and normal frequencies, you would have very little recourse in general but to compute them explicitly by finding the eigenvalues and eigenvectors of the appropriate matrix. However, as a general rule, there are a few observations one can make about the behavior of these normal modes. So, first of all, zero modes appear when we have a symmetry. And that, of course, is something that was clear from our Lagrangian derivation of normal modes and normal frequencies. But something that is slightly less clear but is true is that when you have an approximate symmetry, you have very low-lying frequencies. So the more symmetry you have, the lower the frequency of the corresponding mode. So more symmetric modes have lower frequency. So I will not attempt to make precise exactly what I mean when I say a mode is more symmetric as opposed to less symmetric. But you can see an example of this in the two modes that I described for the linear triatomic molecule. In the case of a linear triatomic molecule, the symmetric mode had a lower frequency than the anti-symmetric mode. And this is a general feature that systems tend to have, that the more symmetry a mode has, the lower its frequency is. Applying that statement is more an art than a science because I'm not going to try and make precise exactly what I mean by a mode with more symmetry as opposed to less symmetry. But indeed, there's a whole mathematics behind approximate symmetries that one can use. And so I think it's important to remember in physics that even if we don't have an exact symmetry, so we don't have any exactly conserved quantities, and we don't have an exact zero mode, it's still very often the case that from a practical point of view, it's useful to find approximate symmetries, find very low frequency or modes which are very long wavelength or low energy compared to other less symmetric modes. Indeed, there's a sense in which the entire field of condensed matter physics, to some extent, is the art of trying to identify the lowest energy excitations of a system based on the symmetries present. So that's a sort of philosophy that underlies a great deal of physics. Are there any questions before I continue? So this really concludes what I had planned to say about systems with many degrees of freedom. But I would like to end today's class with a few comments. So far, I have been considering in this and the last lecture systems with a finite number of degrees of freedom. But many interesting systems have an infinite number of degrees of freedom. And so rather than having a finite number of normal modes and normal frequencies, they have an infinite number of normal modes and normal frequencies. But it is typically the case that many of these normal frequencies will be very, very energetic. They'll be very, very high frequency or very, very short wavelength. So they'll be very high energy. So if you're looking at a system and you're probing it with energies below some scale, then there will be effectively only a finite number of degrees of freedom. And so many systems in physics are described in terms of an infinite number of degrees of freedom, but effectively they can be viewed as systems with only a finite number of degrees of freedom.
What's the example of that?
So let me give you an example. So let's consider a rope. Then a rope is a continuous object. But if you are only interested in an approximate description of the rope, you could approximate the rope as a system of masses that are all connected by some rigid rods of a given length. Now, each of these masses would have a mass m, and each of the links connecting the masses would have a length L, and one is really interested in the limit where the number of masses goes to infinity. But when one takes the number of masses going to infinity, one also takes the length of the link separating them to 0, but you do so in such a way that M and L both go to 0 at the same time, in such a way that M over L is constant and describes the mass density of the rope. So here, for example, I have approximated a piece of rope by 8 masses connected by 7 lengths. But of course, I could approximate it by 27 masses connected by 26 links. And at the end of the day, I want to take all those things to infinity in such a way that the mass per unit length remains constant. And when I do so, I will end up approximating the rope not by a finite number of discrete positions. So the degrees of freedom, if I have 8 masses, will be the 8 positions of those masses. So, for example, I could call them Qi, where I runs from 1 up to n, which would be 8 in this example. And then I would take the limit where n goes to infinity and try and come up with some description which is valid in that large n limit. And such systems are often called field theories. Because rather than considering Qi, where I runs from 1 up to n, I could define a variable phi, which depends on, which I think of as a function of the position of which mass I'm considering. So phi at a given value of xi and t would just be Qi as a function of t. And then in the limit where n goes to infinity, I just think of the dynamical variables as given by some function phi that depends on both x and t. So it would be the position of the rope as a function of both x and t. And then I need to find a way of writing down the dynamics of a continuous variable in this way. So and this description, for example, would be valid whenever I am probing the rope on length scales that are much large compared to this spacing little L between the masses that make up the rope. If those masses are all atoms and these length scales are atomic or molecular distances or intermolecular distances, then this description of a rope in terms of a continuous variable phi that depends on both x and t would be a very useful and practically applicable description of the dynamics of the rope. And so how would I go about describing the dynamics of such a continuous variable? Well, if I have a discrete, a finite number of variables, the way that I would describe their dynamics would be writing an action, which is a functional of the Qi's as a function of t, which would be written as an integral of a Lagrangian that depends on the Qi's, their time derivatives, and time. And what I would like to do then is come up with an action formulation of a theory with continuous degrees of freedom. So that means I need to come up with an action that depends on phi as a function of both x and t. And there are many ways of trying to construct such an action. But it turns out that most systems are effectively described by an action which would be an integral dt dx of a function of phi and its derivatives with respect to both time and x, as well as t and x. And that quantity, which I integrate over time and space, as opposed to just time, is known as the Lagrange density, as compared to the Lagrangian, which is something you integrate only over time. So in studying the dynamics of systems with large numbers of degrees of freedom, we use exactly the same Lagrangian formulation. We write down Euler-Lagrange equations. We study functional derivatives. We construct conserved quantities just as we did in classical mechanics, except instead we consider our dynamical variables to be functions of space as well as time. Now, what is a classical object that you are familiar with, which is a function of space? Well, the one classical object that I know you have spent at least a couple semesters of your life studying, which is a function of both time and space, is the electric field and the magnetic field. So, for example, if you want to write down Maxwell's equations in an action formulation, then you would need to write down an action for the electromagnetic field, which would be an integral. Now your electromagnetic fields live in a three-dimensional space as well as time. So integral dt, d3x of something which would be the Lagrange density of the electromagnetic fields. And I don't know if you've seen, you will see it in your electromagnetism class, I believe. But for example, for the electromagnetic fields, the appropriate Lagrangian is E squared minus B squared. And if you vary this action with respect to the E and B, you'll derive Maxwell's equations. And so, for example, this would be an example of a system with continuous degrees of freedom, which can be formulated in terms of an action principle, just as all of the systems with finite numbers of degrees of freedom. And I believe, I don't know if you'll cover that in your electromagnetism class. Are you taking an electromagnetism class this semester? Did you cover this in your electromagnetism class? Okay, well, there you have it. Okay, so I guess you didn't cover it in your electromagnetism class, but now you know. So did you guys see the electromagnetic field strength? The electromagnetic field strength tensor in your electromagnetic? Okay. Did you? You still have a semester of E&M left to go. Okay, you'll see it next fall. You see the field. Have you guys seen the field strength? Or you will see the field strength? You threes have seen the field strength. Okay. Well, this also can be written in terms of the field strength, but that's not important. The important thing is that there is an action for electromagnetism, just as there is an action for a point particle, just as there's an action for everything else. So perhaps I should stop now. Are there any questions before I conclude? Now let me think for a second. Yeah, no, there is a minus sign. I was worried that I got a sign wrong, but there is a minus sign there. Yeah. Good. No questions before I conclude? Okay. I'll see you next Tuesday.